Once we've calculated the concentration of our standard dilutions, as we did in the previous video, we need to measure the absorbances of these samples at lambda max. For our samples in the lab, lambda max will be measured at 450 nanometers. But for this example, we're measuring absorbance of a different compound, right? It's an arsenic compound. So that's naturally going to have its own lambda max, and it's also going to have its own molar absorptivity, which is also referred to as extinction coefficient or just epsilon value. This value reflects the strength of the absorbance at whatever lambda max is, and our goal is to find that value. So let's enter the absorbance values into this CoLab notebook the exact same way that you'll enter your absorbances for the iron content lab. Once the table is complete with all the concentrations and absorbances for all of our standards, we can use the next block of code to plot the calibration curve. So the epsilon value that I mentioned earlier is going to be the slope of our linear regression plot, and it's needed so that we can calculate the concentration of our experimental sample by simply measuring the absorbance of it. And then we can plug in that absorbance into the equation of the line, y equals mx plus b, that we're getting in this step. Here I get a molar absorptivity of 434. That'll be units of inverse molar, inverse centimeters, but you'll likely get something different because your system is based on iron, not on arsenic like this one. So here we've obtained the line of best fit, and it can be used to solve for the unknown concentration of arsenic in our water, but you'll use yours to calculate the concentration of iron in your prepared samples from cereal.